Hello friends, in our previous discussion we talked about work energy theorem, linear momentum and its conservation, the Newton laws, and we also talked about impulse and kinetic energy. Carrying forward our discussion on Newtonian mechanics, today we shall be talking about potential energy. Potential energy of a system. So far in our discussion on energy, we have defined a system in general, but have focused our attention primarily on single particles or objects under the influence of external forces. Let us now consider systems of two or more particles or objects interacting via a force that is internal to the system. The kinetic energy of such a system is the algebraic sum of the kinetic energies of all members of the system. There can be systems, however, in which one object is so massive that it is modeled as stationary and its kinetic energy can be neglected. For example, if we consider a ball earth system, as the ball falls to the earth, the kinetic energy of the system can be considered as just the kinetic energy of the ball. The earth moves so slowly in this process that we can ignore its kinetic energy. On the other hand, the kinetic energy of a system of two electrons must include the kinetic energy of both particles. Let us imagine a system consisting of a book and the earth interacting via the gravitational force. We do some work on the system by lifting the book slowly from rest through a vertical displacement delta r, and it is equal to yf minus yi. According to our discussion of work as an energy transfer, this work done on the system must appear as an increase in energy of the system. The book is at rest before we perform the work and is at rest after we perform the work. Therefore, there is no change in the kinetic energy of the system. Because the energy change of the system is not in the form of kinetic energy, it must appear as some other form of energy storage. After lifting the book, we could release it and let it fall back to the position yi. Notice that the book and therefore the system now has kinetic energy and that its source is in the work that was done in lifting the book. While the book was at the highest point, the system had the potential to possess kinetic energy, but it did not do so until the book was allowed to fall. Therefore, we call the energy storage mechanism before the book is released potential energy. We will find that the potential energy of a system can only be associated with specific types of forces acting between members of a system. The amount of potential energy in the system is determined by the configuration of the system. Moving members of the system to different positions or rotating them may change the configuration of the system and therefore its potential energy. Let us now derive an expression for the potential energy associated with an object at a given location above the surface of the earth. Consider an external agent lifting an object of mass m from an initial height yi above the ground to a final height yf. We assume the lifting is done slowly with no acceleration. So, the applied force from the agent is equal in magnitude to the gravitational force on the object. The object is modeled as a particle in equilibrium moving at constant velocity. The work done by the external agent on the system, that is object and the earth, as the object undergoes this upward displacement is given by the product of the upward applied force F applied and the upward displacement of this force delta r is equal to delta y. Therefore, net work done is equal to F applied into delta r and is equal to mg into yf minus yi and is again equal to mg yf minus mg yi. This result is the net work done on the system because the applied force is the only force on the system from the environment. Note here that the gravitational force is internal to the system. Also notice the similarity between this equation and the work kinetic energy equation. In each equation, the work done on a system equals a difference between the final and initial values of a quantity. In work kinetic energy equation, the work represents a transfer of energy into the system and the increase in energy of the system is kinetic in form. In equation A, the work represents a transfer of energy into the system and the system energy appears in a different form, which we have called potential energy. Elastic potential energy. Because members of a system can interact with one another by means of different types of forces, it is possible that there are different types of potential energy in a system. We are familiar with gravitational potential energy of a system in which members interact via the gravitational force. Let us explore a second type of potential energy that a system can possess. Consider a system consisting of a block and a spring as shown in the figure. The spring force is the interaction between the two members of the system. The force that the spring exerts on the block is given by Fs is equal to minus Kx. The work done by an external applied force on a system consisting of a block connected to the spring is given by this equation, where work done is equal to half Kxf square minus Kxi square. In this situation, the initial and final x coordinates of the block are measured from its equilibrium position, that is x is equal to 0. Again, as in gravitational case, we see that the work done on the system is equal to the difference between the initial and final values of an expression related to the system's configuration. The elastic potential energy function associated with the block spring system is defined by elastic potential energy is equal to half Kx square. The elastic potential energy of the system can be thought of as an energy stored in the deformed spring, one that is either compressed or stretched from its equilibrium position. The elastic potential energy stored in a spring is 0 when the spring is undeformed at x is equal to 0. Energy is stored in the spring only when the spring is either stretched or compressed. Because the elastic potential energy is proportional to x square, we see that elastic potential energy is always positive in a deformed spring. Everyday examples of the storage of elastic potential energy can be found in old style clocks or watches that operate from a wound up spring and small wind up toys for children. When a block is pushed against the spring by an external agent, the elastic potential energy and the total energy of the system increases. When the spring is compressed a distance acts maximum as shown in figure C, the elastic potential energy stored in the spring is half kx square maximum. When the block is released from rest, the spring exerts a force on the block and pushes the block to the right. The elastic potential energy of the system decreases, whereas the kinetic energy increases and the total energy remains fixed. When the spring returns to its original length, the stored elastic potential energy is completely transformed into kinetic energy of the block as shown in figure E. Conservative and non-conservative forces. We now discuss about a third type of energy that a system can possess. Imagine that the book as shown in figure has been accelerated by your hand and is now sliding to the right on the surface of a heavy table and slowing down due to the force of friction. Suppose the surface is the system, then the friction force from the sliding book does work on the surface. The force on the surface is to the right and the displacement of the point of application of the force is to the right because the book has moved to the right. The work done on the surface is positive, but the surface is not moving after the book has stopped. Positive work has been done on the surface, yet there is no increase in the surface kinetic energy or the potential energy of any system. From your everyday experience with sliding over surfaces with friction, you can probably guess that the surface will be warmer after the book slides over it. The work that was done on the surface has gone into warming the surface rather than increasing its speed or changing the configuration of a system. We call the energy associated with the temperature of a system its internal energy, symbolized E internal. In this case, the work done on the surface does indeed represent energy transferred into the system, but it appears in the system as internal energy rather than kinetic or potential energy. Now again consider the book and the surface together as a system. Initially, the system has kinetic energy because the book is moving. While the book is sliding, the internal energy of the system increases. The book and the surface are warmer than before. When the book stops, the kinetic energy has been completely transformed to internal energy. We can consider the work done by friction within the system, that is, between the book and the surface, as a transformation mechanism for energy. This work transforms the kinetic energy of the system into internal energy. Similarly, when the book falls straight down with no air resistance, the work done by the gravitational force within the book earth system transforms gravitational potential energy of the system to kinetic energy. Figures B, C and D show energy bar charts for the situation in figure A. In figure B, the bar chart shows that the system's kinetic energy at the instant of the book is released by your hand. We define the reference amount of internal energy in the system as 0 at that instant. Figure C shows the kinetic energy transforming to internal energy as the book slows down due to the force of friction. In figure D, after the book has stopped sliding, the kinetic energy is 0 and the system now contains only internal energy. Notice that the total energy bar in red has not changed during the process. The amount of internal energy in the system after the book has stopped is equal to the amount of kinetic energy in the system at the initial instant. This equality is described by an important principle called conservation of energy. Now consider in more detail an object moving downward near the surface of the earth. The work done by the gravitational force on the object does not depend on whether it falls vertically or slides down a sloping incline with friction. All that matters is the change in the object's elevation. The energy transformation to internal energy due to friction on that incline, however, depends very much on the distance the object slides. The longer the incline, the more potential energy is transformed to internal energy. In other words, the path makes no difference when we consider the work done by the gravitational force, but it does make a difference when we consider the energy transformation due to friction forces. We can use this varying dependence on path to classify forces as either conservative or non-conservative. Of the two forces just mentioned, the gravitational force is conservative and the friction force is non-conservative. Conservative forces. Conservative forces have these two equivalent properties. The work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. The work done by a conservative force on a particle moving through any closed path is 0. A closed path is one for which the beginning point and the end point are identical. The gravitational force is one example of a conservative force. The force that an ideal spring exerts on an object attached to the spring is another. The work done by the gravitational force on an object moving between any 2 points near the earth's surface is given by this equation, where Wg is equal to minus mg into yf minus yi and is equal to mg yi minus mg yf. From this equation, notice that Wg depends only on the initial and final y coordinates of the object and hence is independent of the path. Furthermore, Wg is 0 when the object moves over any closed path, that is, where yi is equal to yf. For the case of object spring system, the work done by the spring force is given by Ws is equal to half kxi square minus kxf square. Here we see that the spring force is conservative because Ws depends only on the initial and final x coordinates of the system and is 0 for any closed path. Non-conservative forces. A force is non-conservative if it does not satisfy properties 1 and 2 for conservative forces. The work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. The work done by a conservative force on a particle moving through any closed path is 0. We define the sum of kinetic and potential energies of a system as the mathematical energy of the system as given by this equation. E mechanical is equivalent to K plus Pe. Here K includes the kinetic energy of all moving members of the system and Pe includes all types of potential energy in the system. For a book falling under the action of the gravitational force, the mechanical energy of the book earth system remains fixed. Gravitational potential energy transforms to kinetic energy and the total energy of the system remains constant. non-conservative forces acting within a system, however, cause a change in the mechanical energy of the system. As an example of the path dependence of the work for a non-conservative force, consider the figure shown here. Suppose you displace a book between 2 points on a table. If the book is displaced in a straight line along the blue path between points A and B, you do a certain amount of work against the kinetic friction force to keep the book moving at a constant speed. Now imagine that you push the book along the brown semicircular path. Here you perform more work against friction along the curved path than along the straight path because the curved path is longer. The work done on the book depends on the path, so the friction force cannot be conservative. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. The elastic potential energy stored in a spring of force constant K is given by half kx square. A force is conservative if the work it does on a particle that is a member of the system as the particle moves between 2 points is independent of the path the particle takes between the 2 points. Furthermore, a force is conservative if the work it does on a particle is 0 when the particle moves through an arbitrary closed path and returns to its initial position. A force that does not meet these criteria is said to be non-conservative. So that is it for today. See you in the next lecture with more on Newtonian mechanics. Thank you very much.